This is stochastic process, Mod-05 continuous time Markov chain, and this is a 7th lecture, communication systems. In the last 6 lectures, we have discussed the continuous time Markov chain, and in the last 2 lectures, we have discussed the application of a continuous time Markov chain in queuing modeling. In this lecture, I am going to discuss the application of continuous time Markov chain in communication systems. So, this talk divided into 3 parts. The first I am going to discuss the application of CTMC in 2G cellular network system, and then I am going to discuss the 3G cellular network system. 2G means a second generation and 3G means a third generation cellular network system. And finally, I am going to discuss the simulation of queuing systems. That is basically a discrete event simulation. The cellular system or wireless system is nothing but a network system in which the calls are generated and calls are occupied for some time and leave the system. And this consists of many cells. Each cell is of the hexagonal shape, and our interest is to study the performance analysis of cellular networks using continuous time Markov chain. This is the center cell, and all other 6 cells are called the neighbor cells. Either we can make the performance modeling for the whole cellular networks, or we can make the model for only one cell first, then we can apply the hierarchical modeling for the whole cellular networks. So, in this I am going to discuss the performance analysis of one cell in a cellular networks. Cellular networks or wireless networks, our interest is to study the performance analysis. Suppose you think of a bandwidth as the channels. Whenever some calls originated, it uses the one cell for the one channel for the communication. Suppose you assume that we have a finite number of bandwidth or a finite number of channels in one cell. Suppose that you make it as some capital N finite quantity. So, whenever the calls originated, then it will take one channel from the cell, and the call will be for random amount of time, it will be keep going, and once the call is completed, then the channel will be released. We have designed calls with the 2 types of calls. One is called the handoff call, the other one is called the new call. Handoff call is nothing but a call in progress handed over to another cell due to user mobility. In that case, the channel in old base station, that is in the previous cell, is released and ideal channel given to the new base station. So, that is the way the handoff phenomena operates. Therefore, I consider the call into 2 types of call. One is called the handoff call, the other one is a new call. Handoff call is nothing but the call originated from the neighbor cells and coming into the cell where we are studying. That means, suppose the calls are originated in these neighbor cells and coming into the underlying cell which we are considering, then that calls are called the handoff calls. So, either it can come from this cell to this cell, or it can come from this cell to this cell, and so on. So, therefore, the calls originated from the neighbor cells and coming into the underlying cell, that is called the handoff calls. Whereas, the calls originated within the cell itself, that call is called the new calls. That means the channel will be channel will be given from the same base station of the cell, and once the call is get over, then the channel will be released. Therefore, the calls originated from the neighbor cell is called handoff calls. The calls originated within the cells are called the new calls. These are all the two types of calls coming into the system. If there is a bandwidth or channel, then the calls will be allotted, and after the calls are completed, the channel will be released. So, there are two types of call completion also. Either the call is completed within the cell itself, not moving anywhere. Due to mobility, there is a possibility the calls can be originated within the cell or coming from the neighbor cell. It can last for a whole time in the cell, and it would have moved to the other cell also. In that case, it is called the handoff to neighbor cells. The way the calls are originated from the neighbor cell coming into the cell, the same way you can discuss the outgoing also. The calls can be completed within the cell itself, or it's keep going to the neighbor cells. That is called the handoff out calls. Now, I am going to discuss what is the concept of dropping and blocking probability. Since the handoff calls are having the higher priority, because the calls are already originated and keep coming into the cell, and there is a possibility it can move into the other cell also. Therefore, we should give a higher priority to the handoff calls. There are many ways of giving the higher priority to the handoff calls. The one easy way is reserve few channels for the handoff calls. That means out of capital N channels, you reserve few channels for the handoff calls, not physically few channels. Whenever you have left out a few channels in the system, in the pool, then if that number is more than the reservation, then you keep allowing the new calls as well as handoff calls. If you reserve some number of channels for the handoff calls, and the available bandwidth or available channels at a time of arrival, it is less than that, then do not allow the new calls. So, only the handoff calls will be allowed whenever the number of available channels are going less than or equal to the prescribed number. So, that is called a fixed reservation channel policy. So, suppose out of capital N channels, you reserve some G channels for the handoff calls. That means if a number of ideal channels less than or equal to G, then the new call will be blocked. Whereas at the time, if the handoff calls enter into the system, then it will be channel will be allocated. If no ideal channel is available, that means all the channels are busy with calls, then handoff calls will be dropped. Obviously, new calls also will be dropped if no channel is available, but if the number of ideal channel is less than or equal to G itself, from that point onwards, the new calls will be blocked. So, our interest is to find the blocking probability and the dropping probability. So, the dropping probability is nothing but the handoff calls are dropped because of no ideal channel in the system. The blocking probability is nothing but the probability that the new calls are blocked because the number of ideal channels are less than or equal to G. Once we are able to find out these two performance measures, then using that one can design better cells, how to for a given number of channels, how we can reduce the blocking probability as well as the dropping probability. So, these measures we are going to find out using a continuous time Markov chain. So, for that we are going to make the few assumptions, so that the underlying stochastic process will be a continuous time Markov chain. And here we are making a model for only the one cell, not the whole cellular networks. So, we make the assumption the calls are in a Poisson process for the new calls as well as the handoff calls, and both are independent. We make the rate lambda 1 is the arrival rate for the new calls and the lambda 2 is the arrival rate for the handoff calls, and both are independent. Therefore, the call arrivals, either it is a new call or handoff calls, that will be a sum of two Poisson. Therefore, that is also Poisson process with a parameter lambda 1 plus lambda 2. And also we make assumptions over the call completion, either the call completed within the cell, that is exponentially distributed, the time for the call completion within the cell, that is exponentially distributed with the parameter mu1, as well as the calls handoff to other cells, that is also exponentially distributed with the parameter lambda 2, sorry mu2. And we make the assumptions the call completion as well as the handoff to other cells, that is also independent. And we have a total number of n channels is capital N. Out of that we reserved G channels for the handoff calls, and these channels are called the God channels. So, with this assumption, that means we are considering only one cell, and the new calls from that stream is a Poisson stream, and this stream is also Poisson stream, and the call duration, either call completion is exponential distribution or handoff to the neighbor cells, that is also exponential distribution, and we have total number of n channels. Out of that G is for the reserve channel, and accordingly the Markov chain, first we are going to make a stochastic process. Stochastic process is a CT, that is nothing but the number of busy channels, or each channel is allocated for one call. Therefore, at time t, what is the number of calls, that is the stochastic process, that is a random variable. So, over the t, that is a stochastic process, and since it is a number of busy channels, therefore, it is a discrete state continuous time stochastic process. With the assumptions we have discussed in this slide, the stochastic process will be a continuous time Markov chain. Only nearest neighbor transitions are allowed. Therefore, this is not only a continuous time Markov chain, as a special case of continuous time Markov chain, that is a birth death process also. So, it is a variation of MMCC queuing model with the rates are different. That means the birth rates are lambda till n minus g minus 1, n minus g. After that the birth rates are lambda 2. If you recall, this lambda is nothing but lambda 1 is the arrival rate for the new calls, and lambda 2 is the arrival rate for the handoff calls, and lambda here it is lambda 1 plus lambda 2. That means whenever the number of busy channels, it is starting from 0 to n minus g minus 1, both new calls as well as handoff calls are allowed into the system. Therefore, the arrival rate is lambda, birth rates are lambda, whereas the number of busy channels from n minus g to n minus 1, the birth rates are only lambda 2, because the new calls are blocked. Only handoff calls are allowed whenever the system size is n minus g to n minus 1. Whenever the number of busy channels is 1, 2 and so on till n, either the call is completed or the calls are handoff to the neighbor cell, and both are exponentially distributed with the parameters mu1 and mu2 respectively, and both are independent. Therefore, the rates are going to be mu1, mu2 and so on, where mu1 is nothing but so here is some notational problem. This should be this is nothing to do with the mu1 and mu2 which I have defined earlier, that should be mu h and mu n, where mu1 is equal to 1 times mu h plus mu n, and mu t is nothing but 2 times mu h plus mu n and so on. So, this is the death rates. Therefore, the number of busy channels at any time, that is a birth death process with the birth rates lambda till n minus g minus 1, after that it is a lambda 2, and the death rates are n times mu, where mu is nothing but mu 1 plus mu 2. Either I can use this notation or the other notation. Once I know the underlying stochastic process is the birth death process, and that too it is a finite state, and also it is irreducible. So, therefore, all the states are positive recurrent. So, I can solve the PQ is equal to 0 and the summation of PA is equal to 1. I can get the steady state or equilibrium stationary probabilities. So, if I solve this system of equation with the summation of PA is equal to 1, I will get the PIs, where PA is in terms of initially P naught, and the P naught is 1 divided by this. So, this result is uptime is available in this following paper. Here the lambda is nothing but lambda 1 plus lambda 2, and mu is nothing but mu 1 plus mu 2, and those mu i's are n times mu, and A is nothing but rho, that is lambda by mu here, and A1 is lambda by mu, because the birth death process with the birth lambdas and after that lambda 2. Therefore, you have a different expression for 0 to n minus g and n minus g to capital N, you have a different expression for the PNs. So, this is the steady state probability. Once you know the steady state probability, our interest is to get the dropping probability and blocking probability. Dropping probability is nothing but the handoff calls are dropped because of the system size is full. That means all n channels are busy. That means the system, when the system size is in capital N, then the new calls are dropped. Therefore, the dropping probability is equal to the probability that n customers in the system. Here n is nothing but the number of channels. Capital N is the number of total number of channels, all are busy. Therefore, the P suffix n will be the dropping probability. Blocking probability is related to the new calls. So, the new calls are blocked, it is not even enter into the system whenever the number of available channels are less than or equal to g in the system. Therefore, when the system size is from n minus g to capital N, the new calls are blocked. Therefore, the blocking probability is running from n minus g to n p suffix n, that will be the blocking probability. If we made the summation over the steady state probability which we got it in the previous slide, substitute those things, so that will be the blocking probability. Now, I am moving into extending the same logic into 3G wireless networks. So, here also we are making a model for only one cell, and not only one type of calls, we have three types of calls. One is the voice call, the second one is the video call, and the third one is the data call. In the 2G networks, we have only one type of call, that is a voice call, and the voice calls are subdivided into two types, handoff calls and the new calls. So, here also the voice calls are divided into new calls and handoff calls, because we are considering a performance model for a one cell, and the calls could be a voice call, could be a new call or the handoff calls. The video calls, again we are dividing into two types. One is the hard QoS video 1 type call, and the soft QoS, that is video 2 calls, because there are some video calls it is a hard QoS, that means it will not tolerate the delay, the video conferencing live program and so on. So, that type of video calls are the video 1, whereas the video on demand, that can tolerate the delay. So, that type of call is called the soft QoS calls. So, this is a video call, that type is called the video 2. Then the last data traffic, that also can be classified into new call and handoff calls. So, here the priority is the voice calls are the higher priority, then the video 1 call, then video 2, then the data. So, the way we have discussed the 2G cellular networks, we are extending the same idea into 3G wireless networks with the 3 types of calls with this priority, and the priority is taken care with the fixed guard channel policy. Earlier we have only one voice type call, now we have 3 types of calls, therefore the reservation also changes accordingly. And instead of only one voice call, we have 3 types of, therefore the number of channels allocated to different calls also changes. So, in this scenario we have taken voice calls uses only one channel, whereas the video calls that needs more bandwidth, therefore assumption we have made an assumption 4 channels are needed for the video calls, and the data traffic needs only one channel. Therefore voice and so this is explained in this paper in detail. So, here we made the assumption the call arrivals Poisson process. The usual way is 2G networks call arrivals are Poisson process, call holding times are exponential distribution and so on. But what we are making the extending the model with the one channel is needed for voice and data traffic, and the 4 channels are needed for the video 1 and 2 traffic, and the priority is voice, then video 1, then video 2 and data. And since the priority is there, we are reserving a HI number of channels for the handoff calls in this order, and the NI channels are reserved for the new calls of voice and video 1 and 2, and there is no reservation for the new data traffic calls. And we allow the retry of the calls of a new voice and the video 2 and the data traffic. Therefore, the proposed model, instead of a Poisson, we have a Markov arrival process for the data arrival, and instead of exponential distribution we have more general situation, that is a phase type distribution for the holding time, call holding time. And whenever the calls that are blocked, it can go to the orbit and it can retry, and the retrial times also assumed to be a Poisson distribution. And since we have made the reservation for the calls with the HIs and NIs, accordingly these total number of channels are divided into many parts, and the calls will be allotted according to this priority. That means from 0 to M7 the handoff voice will be allotted from 0 to M, whereas the new voice will be allotted till the number of busy channels going from 0 to M7, because H1 is a reservation for the handoff voice call. So, like that this is the higher priority, then next priority and so on, and this is the new data call, and there is no priority for the new data. Therefore, this is the lowest priority call traffic, and this is the corresponding queuing model. You can compare the queuing model of the 2G networks with the 3G networks. Since we have 3 types of calls, that is voice, video 1, video 2 and data traffic. So, we have a different traffic is contenting for the channels in the channel pool, and after the calls are over, then it will either be completed within the cell or hand off to the neighbor cells. The first one is the handoff voice. So, the call admission control scheme allows, then the call will be allotted, otherwise it will be dropped. There is no waiting, there is no orbit, the calls blocked won't go to the orbit and wait. Whereas the new voice call, if there is no channel, then it will go to the orbit, with some probability it will again retry after phase type distributed time, which we have made the assumption, otherwise it will quit with the 1 minus this probability. Similarly, for the handoff video 1, either it will be accepted or it will be dropped, whereas the new video 1 also, either it is we use the word dropped for the handoff and the blocking for the new type, new calls. Therefore, new video call, video 1 call will be blocked if there is no bandwidth. Whereas the video 2, if there is no bandwidth, then it will go to orbit with some probability it will come back, with 1 minus of this probability it will quit. Similarly, the new video 2 also, either it will get accepted if the channel is available, the required number of channels are available, otherwise it goes to the orbit and retry. The third type, that is a data, both the new and the handoff data, either it will be accepted or it will go to orbit and come back. So, it is similar to video 2, but the difference is the video takes 4 channels at a time, whereas the data and the voice takes only 1 channel at a time. So, this is the corresponding queuing model for the 3G wireless networks, cellular networks for only one cell. So, here the stochastic process is the state of the cell. What is the number of channels are available at that time t, that is going to be the stochastic process over the time, and this will be modeled as a quasi birth death process, whereas the 2G wireless cellular networks is we modeled as a birth death process. So, here this is a quasi birth death process. So, what is the meaning of quasi birth death process? This is a generalization of birth death process. Here the Markov chain with the state space S, and the state space can be divided into k levels, and each level you have a capital M states or M phases. Suppose you have a capital M phases and we have a k levels in it. So, it is a generalization of birth death process, means suppose the system is in some ith level and some state, then there is a possibility it can go to the I minus 1th level with the different states, or I plus 1th level in the different states, and so on. Therefore, here the state space is divided into k levels, and each level has the some finite number of, need not be the same number, each level should have some finite number of states. So, it is a generalization of birth death process. Accordingly, you have a state space with this type of vector, and you can study in detail in the particular paper about how to obtain the performance measures. And here I am listing what is the meaning of I, J, K, L, and what is the meaning of US, and what is the meaning of S suffix, and so on. And the last one, what is the meaning of RL, means the phase of retrial of calls in orbit. So, here also we uses the difference between the birth death process and the quasi birth death process. The Q matrix consists of block matrices, whereas in the birth death process the Q matrix is a tridiagonal matrix, and each entries are the elements, whereas here each entries are the matrix, and the elements of that matrix also again will be a matrix based on the number of levels. And in this model we have a 4 level quasi birth death process. Therefore, we have a Q matrix with the block matrices in 4 levels, and the 4th level you have the matrix with the entries are the elements. I am just skipping this part of how the generator matrix, each element, each matrix exists. And our interest is to get the steady state distribution for the quasi birth death process also. So, here I am making the assumption the quasi birth death process is ergodic, therefore, the steady state distribution exists. This is a generalization of birth death process, therefore, the Markov chain, whatever the steady state distribution condition you need, the same condition you can cross check. So, here this QBD is ergodic, therefore, a steady state distribution exists. Then you can solve the x times Q matrix equal to 0 with the x times E vector that is equal to 1, using that you can get the steady state probability vector. And since it is a QBD, you can use the matrix geometry technique, that is a well known technique for the QBD, we can use that and get the steady state probabilities. And these are all the, once you know the steady state probability, you can get the blocking and the dropping probabilities. Since we have 3 types of calls, we can analyze the blocking and the dropping probabilities for the various traffic, and also we are discussing the retrial and orbit and so on. So we can find out the probability that the new voice handoff video to new video to handoff data and the new data calls join orbit. What's the probability for that? You can find out after getting the steady state probabilities. So you can, one can see the paper to understand the complete paper. And also one can discuss the special cases by making the simpler assumptions. The last assumption is a Poisson arrival exponential service and no trial, and one type of call that will land up into the 2G cellular networks which we have got it. So if you make a subsequent special cases, you will end up with the blocking probability and the dropping probability which we have discussed in the second generation cellular networks. Now I am moving into the last part of module 5 continuous time Markov chain. In this I am going to discuss the simulation of queuing systems. So the module 5 continuous time Markov chain started with the definition and the properties and so on. Then I discussed the birth death process. Then I discussed the application of a birth death process in simple Markovian queuing models. Then also I have discussed the queuing networks, that is also a multidimensional continuous time Markov chain as application. And finally I have given few practical application in cellular networks for the performance analysis. Now I am going to discuss the discrete event simulation of simple Markovian queuing systems. So in this queuing network modeling lab, one can do discrete event simulation, and the discrete event simulation for the queuing network involves Markovian queues. We can do some experiment over the Markovian queues, and we can do the discrete event simulation for the non-Markovian queues, and one can do the discrete event simulation for the queuing network also, and finally one can do the fluid queues also, one can simulate. But since I have discussed only continuous time Markov chain till now, I am going to do a discrete event simulation for the Markovian queues. So that is in the first 3 experiments. The other 3 experiments are related to the non-Markovian queues. The first experiment consists of a simulation of a MM1 queue, single server queue, and a MMC finite server queues, and the infinite server queue. So in the sometime I have done the discrete event simulation of a MM1 queue. So let me go for MMC finite server queue. So in these you need the input of arrival rate, input of the departure rate, and the number of servers. It is a multi-server infinite capacity model. So suppose you choose the arrival rate is 2 and the service rate is 3 and the number of servers are 2. That means it is a MM2 infinity model with the arrival rate 2 and the service rate is 3. So one can start the discrete event simulation by clicking the start. Then you will get the window of so this is the sample path over the time, what is the system size. So at this time point 1 arrival comes, then 2, then service is completed, and so on. So this is the sample path over the time, and here you can get the performance measures. So whatever I have discussed, the performance measures of a steady state distribution and all other performance measures, one can get it with the theoretical results in the third column. whereas the second column gives the running time till the discrete event simulation runs for 15 time unit, and what is the result for the mean number of systems and so on, and this will converge to this value for t tends to infinity. So, I make sure that this arrival and departure rates are satisfying the condition, so that the steady state distribution exists. Therefore, as a t tends to infinity, this will reaches the steady state theoretical result. If you change the value arrival rate and the departure rate something else, then there is a possibility if the conditions for the stationary distributions are not satisfied, then still the runtime results you will get, but that will not be converged to the theoretical, and also the steady state results will not be possible. It will be a dash here. So, as long as the steady state distribution those conditions are satisfied, then you will have the results in the third column, otherwise you will not have the results here. So, now you can see the throughput till this much time you are getting 2.0, whereas the steady state throughput is 2. Throughput is nothing but the number of customers served per unit time. Like that one can get the throughput, utilization, average response time or mean sojourn time, and mean waiting time in the queue. So, using Little's formula used to find out this quantity. So, this quantity you can get it from the discrete event simulation at any time as well as the theoretical result, and this is the mean number of customers in the system, that is E n, and the mean number of customers in the queue, that is EQ, which we got it. So, this result one can see the discrete event simulation as well as a t tends to infinity, what is the theoretical result if the conditions for the stationary distribution satisfied. And here this information is how many calls are entered, how many customers enter into the system, and how many are served, and how many customers are blocked. Here there is no blocking because it is an infinite capacity system, and we are considering the retrial orbit and so on. Therefore, here it says number of orbit customers is 0, but this is not necessary. This is irrelevant information in the MMC queuing model. Now, let me go back and do the live simulation of infinity. So, here you have to provide only the arrival rate and the service rate, because the number of servers are infinite. It's a self-service system. You can cross check the theoretical results are correct and so on. So, here I am getting the steady state result based on the theory, whereas this is the runtime results. There is no blocking probability because the system infinite capacity. Mean number of customers in the queue, that is 0, and here also 0 because it is a infinite server. Therefore, customers who enter into the system immediately will get the service. Therefore, the queue average number of customers in the queue, that is 0, and the average time spending in the queue, that is also 0. That is correct. There is no blocking, and utilization is what is the probability that the servers are utilized. Now, let me go to the next experiment, that is second experiment for the finite capacity queuing model, whereas the first experiment is the infinite capacity queuing model. So, in this we have we need to give the arrival rate, service rate, and the number of servers. You can go for the multi-server MMCN model. You can give one also. You can give infinite servers also one can give. So, here the number of servers, suppose you fix it 3 and the capacity is 4, you can do the simulation. So, the blocking probability in the runtime, there is at this time it does not cross the number 4. Therefore, the blocking probability is 0 in the runtime result, whereas the theoretical steady state result says the blocking probability is 0.005. So, whenever the system touches 5, then you will have the blocking probability in the runtime. So, this is a discrete event simulation. See, number of customers blocked is till now 0, therefore, you are getting the blocking probability 0 at this runtime. Suppose you run it again, let us see. Now also it does not crosses the system size by 2. So, maybe I can reset with the number of servers I can put 2 and the capacity is 3. So, the blocking probability is this much, the capacity of the system So, there is no arrival after crossing, therefore, still you are getting the blocking probability is 0, whereas the steady state theoretical result says 0.037. So, one can simulate with the different parameters and you can see the sample path. So, this is the sample path for MM23 queuing system with the arrival rate 2 and the service rate is 3. Yeah, now we are getting the blocking probability because the system crosses, touches the capacity 3, therefore, some calls are blocked, some customers are blocked, therefore, the blocking. So, you can find out from here number of customers 44 entered and 4 are blocked, therefore, that ratio will be the blocking probability because it is a discrete event simulation. Now, let me go back and go to the experiment 3. Experiment 3, we have a retrial model with the bulk arrival and bulk service. So, now it is no more a birth death process simulation, this is a non birth death process because you have a bulk arrival and a bulk service was possible and the retrial. Therefore, let me show the simulation. You need some more information. So, what is the arrival rate you have to supply? Suppose if it is a bulk arrival, then you should say what is the distribution, whether the bulk arrival comes in a bulk some constant number or it comes in a some distribution. You can choose it's geometrically distributed. And the parameter for the bulk arrival parameter you can choose some 0.5. Then the departure rate, you can choose the departure rate. It can be a bulk departure or bulk. So, either you can choose a bulk arrival or bulk departure or you can choose both also. The number of servers in the system, suppose there are 2 servers in the system and the capacity system is 4, or you can choose a infinite capacity of the system also. And if you need orbit, then you have to click for orbit, and if you are changing the queuing discipline, the first come first served, last come first served or random order, you can choose the queuing discipline also, accordingly the discrete event simulation goes. So, this is not a birth death process, this is a continuous time Markov chain simulation. With a different queuing discipline also one can go for it. Now, once you start the simulation, yeah, since it is a bulk, we have made a bulk arrival, whereas we made it, we did not click for the bulk departure, therefore, the customers keep going by one whenever the service is over, but since it is a bulk arrival with the arrival distribution is the number of arrivals that is geometrically distributed, therefore, it just jump with the bulk arrival, whereas the departure is by 1 by 1. And here is the performance measures, is the runtime performance measures, and we didn't till now we didn't supply the theoretical steady state or theoretical results for this model. And these are all the different results in the over the runtime. And similarly one can go with the bulk departure, and we can change the queuing discipline also. So this is a discrete event simulation sample path for this scenario. So I can reset, and if I don't want the bulk arrival, and if I choose the capacity of the system is 4, so this will be a no bulk arrival, no bulk departure. Therefore this is a MM2-4 system with a first come first out, and I can go for, instead of first come first out, I can go for the last come first out also. The customer is last entered, he is getting the service first. So this is a steady state, and this is a time dependent result. And I can change again this into inf, that means it is a 2 servers infinite capacity model with the first come first served. Still this is in the testing phase, so some of the things should be removed, some of the things has to be edited, so still it is in the testing phase. So this is the performance measures for the MM to infinity model. So that means in this experiment also you can remove the bulk arrival and the bulk departure part and so on. You can try the simplest simple Markovian queuing model also. One can do the discrete event simulation of that. And since it is an infinite capacity model, the blocking probability is 0. And the steady state throughput is 2, one can find out from the formula also. Whereas the runtime is this. So if this discrete event simulation runs for a longer time, then this will converge to 2. Like that you can discuss the all other results also. All the results will be converges to the steady state theoretical probability, the theoretical results. So with this, let me complete the discrete event simulation of a simple Markovian queuing model, because we are discussing this under the title of application of a continuous time Markov chain. Therefore, I discuss only the Markovian queues. There are some non-Markovian queues and so on. So I am not discussing the non-Markovian queues at this stage. After I discuss the renewal theorem and the Markov regenerative process and SME Markov process and so on, I will be discussing the non-Markovian queuing systems also. So here we have discussed only the simple Markovian queuing system, that is nothing but the applications of a continuous time Markov chain. As a summary, the last 7 lectures we have discussed the continuous time Markov chain from the definition and properties and a few simple continuous time Markov chain, starting with the Poisson process, birth-death process, pure birth process, pure death process, then application of CTMC in the queuing model, starting with the MM1 queue and other simple Markovian queues. Then we discuss a few queuing network which has the product form solution. Then in the last this lecture we have discussed the applications of CTMC in 2G second generation cellular networks as well as the third generation cellular networks. And application of CTMC in the 2G networks is the birth-death process, whereas the applications of CTMC in 3G cellular networks is the quasi-birth-death process. Even though I have not discussed in detail the complete modeling, one can see it from that paper. My intention here is explain the quasi-birth-death process through the applications. and we discussed the stationary distribution and all other performance measures for the birth death process comes in the second generation networks and the quasi birth death process in the third generation networks. And finally, I have given the descriptive event simulation for simple Markovian queuing systems only. There are some more non-Markovian queuing systems, so that I will be discuss in the other models. The references are Grossenari's book and Mehdi book, Kishore Trivedi's book. Thanks.